Alright, so finally we have learned enough about electricity to where you can actually start building circuits. Oh my gosh, this is so exciting. Um, we're gonna do some virtual circuits and we're gonna draw out some circuits, and then here in a couple weeks we'll start building actual circuits. And so um oops, sorry about that. So in order to draw some circuits, you need to know the symbols because, well, every time that I need to represent a light bulb in a circuit, I'm not going to take the time to draw this out. And so in your notes, what I want you to do is pause the video and go ahead and write down these symbols, right? And so they're right below them. So to represent a battery, we have several of these little lines. A wire is just a line. Resistor's got a little bit of a squiggle to indicate some kind of turbulence there for the voltage to drop across it. We also have light bulbs because those are common resistors that we use. We've got junctions where a wire splits, capacitors in case we have those in the circuit, and last but not least switches, which actually break the current and allow it not to flow. And so we have two big kinds of circuits that we're going to work with as well. And these are series circuits and parallel circuits. Now, a series circuit is where the current only has one path, and it flows right around and goes back to the negative terminal of that battery or of that wall socket, if that's what we're using. And then parallel circuits get their name from how they look. However, parallel circuits, the electricity has more than one path through which it can flow. And so what we see is that there's a place where the current actually kind of splits and can go either direction. And so what we see is that it comes back around and they reunite before returning to that negative terminal. Now, a parallel circuit doesn't mean it only splits once. I could add, however many really light bulbs and kind of parallel splits that I wanted to, but at the end of the day, they all come back to that negative terminal. Right? And so what I want you to do is use those symbols to draw a circuit. All right, so a capacitor and a bulb. All right, and so a capacitor is like this, and a bulb, great, is like that. Okay, so what about a battery in a bulb? Well, a battery in a bulb is just those extra lines to indicate that I've got a battery. A battery and two bulbs. So I could draw this in series or I could draw it in parallel. Either way, I got a battery, and I'm going to draw mine in series and two bulbs. Okay. Battery and two bulbs at different junctions. And so this is going to be, again, battery. This will be a parallel circuit. Woo, that's a bad battery. I'm going to split off and do another parallel one there. Good deal. A battery, a switch, and two bulbs. So if I want to add a switch to this, I can just, oh no, it erased some of it. So the switch is only going to be effective if it comes before those lights, and so kind of before that junction I need that switch. A battery, a switch, two bulbs, and a junction, so I've got that. And then a battery, a switch, two bulbs, a junction, a resistor affecting one of the light bulbs. This one's a little more complicated. So let's see. I need a battery, I need a switch, so do battery, switch, junction, and then a resistor that affects one of the bulbs. So I'm going to put a resistor here, and then a bulb, and then back this way, so that current is flowing this way. If I've got that switch open, neither of those light bulbs will come on, but if that switch is closed, that current splits, goes through this resistor before it hits this light bulb, and then all comes back to the negative terminal of the battery. All right, so there's a couple of laws about junctions, and junctions have to do with current going in has to equal current coming out, right? And so if I've got like 5 amps coming in here, it splits to 2 amps, well then I know this has to be 3 amps. And so we kind of talked about that one last time. And Kirchhoff's junction law just says that current into and out of a junction has to be equal. Current is conserved. Kirchhoff's loop law also says that the net change in voltage is 0. And so if I have a battery that's, let's say, 10 volts, I don't even think they make batteries in 10 volts, but that makes my math easy. If I've got a 10 volt battery, right, well, so the battery steps it up 10 volts. And then if I have 2 equivalent resistors, each one of those is going to step the voltage down 5 volts so that the net change throughout the circuit is 0, right? Thus, the voltage of the battery is equal and opposite to the total voltage of the resistors. And then I know, because of that, that I can kind of use an inverse version of Ohm's law to figure out the voltage across those resistors. And I can substitute the EMF in for the delta V of Ohm's law. Okay. Like I said before, there are 2 kinds of circuits. There are series circuits and parallel circuits. Series circuits have a direct flow of current without junctions or branching, and parallel circuits contain branching, right? And so we see less current going through each of these bulbs than we do for these bulbs. And so what I want you to do, and actually what you guys are going to do a little bit tomorrow in class, is you're going to explore building circuits. And so you're going to build series circuits and you're going to build parallel circuits. And I want to just take a second and show you what that's going to look like through this website. Alright, so you're going to come to this website, the Fuse Box, and all this is just a little online simulation about building circuits. I do want you to do at least levels 1 and 2 on Friday. If you want to come back and do level 3, you can certainly do that. And so it'll tell you the instructions up here, and you've got tools over here. And so it says, turn on the light. Click and drag the bulb and the battery into the testing area. Use wires to join them together so that the light comes on and you make an electrical circuit. So I'm going to drag my battery into the test area, and I'm going to drag my light into the test area. And I know current flows from positive to negative. So my first wire is going to go from the positive terminal to one terminal of the battery. And then it needs to go from the other terminal of the light to the negative terminal of the battery to light up my light. And then it tells me, well done, woohoo, okay. And then I go to the next stage. And well, now I've got a battery and a switch, right? And so I know that I'm going to need to do battery, switch, light bulb, and then connect these from positive to the switch, from the switch to the light bulb back to the battery to complete that circuit. And all you'll do is just go through and go through those challenges. I think there's 6 in each level. So when you build these in class, what I want you to be thinking about is, what is the difference between a series and parallel circuit? And so I want you to be thinking about, like I said, the difference between series versus parallel circuits. I want you to notice the brightness of the bulbs in series versus parallel circuits. And I also want you to note what happens when I break a bulb in a series circuit and what happens when I break a bulb in a parallel circuit. You know, what happens to the rest of those bulbs. Because if at any point there is a break in this circuit, well then electricity is not able to flow. And that's all a switch is a break in the circuit. But, well, what happens if this light goes out versus what happens when this light goes out in a parallel circuit? That's the big difference. I'll ask you about it on Monday. So I want to take a second and talk about current and resistance in series circuits. So we'll talk about series circuits first, and then we'll talk about parallel circuits. And so this is just a modification of Ohm's law. Remember, this EMF is like the delta V for a battery, the voltage difference in a battery. And so if I have 2 resistors in series, To get the total resistance, which is what I use for Ohm's law, all I need to do is add the total add the resistance of each resistor and treat it like one. And so, for instance, if I have like a 2 ohm resistor and a 3 ohm resistor, well then I can just say that's like having one 5 ohm resistor, and I can use Ohm's law down here accordingly, right? And so, for the purpose of your notes, when I am taking resistors in series, all I need to do is add their resistance to get the total resistance for that circuit. However, oh, I'm sorry. So this is what the Ohm's law looks like, the EMF of the battery, and then over the total resistance, and I just add those together if it's a series circuit, if that current doesn't branch at all. However, if that current does branch, right, then I've got, let's say I have 5 amps here. If this is equal, then I have 2.5 amps going to each one, and that's going to be a little bit different. And so if they have the same amount of current, what can I say about their resistance? Well, I can say that their resistance is the same. And so what happens is if I'm trying to find the equivalent resistance for resistors in parallel, I'm looking at this, right? To find the equivalent resistance, I take 1 over the resistance of each. So again, if I have like a 2 ohm and a 3 ohm resistor, then what I'm dealing with is, let's say like a 10 volt battery again. I would use Ohm's law right here, and I would say that the total current flowing through this circuit is equal to the 10 volts, the EMF of the battery, times 1 over 2 ohms plus 1 over 3 ohms. And I'll have to do a little bit of fraction addition here, or I could reduce these to decimals and add them together that way if I wanted. But for me, I would get a common denominator, and so like I know this is a common denominator of 6, and so I would change this fraction to, what would it be, 3 over 6, and I would change this one to 2 over 6, and well, 3 plus 2 is going to be 5 over 6, so I'm looking at 10 volts times 5 over 6 ohms to get the total current in that circuit. Right? And so again, equivalent resistance here is equal to 1 over this raised to the -1. The equivalent resistance for resistors in parallel is always less than any one resistor, and so that's the other clue. Like if I've got 3 ohms and 2 ohms, then I know my total resistance is less than 3 and it's less than 2. And so when I come up with that, I should get that. Like I had 5/6 after I add them together, and well, 5/6 doesn't even equal 1, and so I know that's a reasonable equivalent resistance for that circuit. A couple of the last things I want to talk about is in your textbook, you'll see a couple of abbreviations for devices, or you'll see words saying like, okay, Johnny plugs an ammeter into a circuit. Well, an ammeter is just a device that measures how much current is going through a wire at any given point. And so I can plug an ammeter in and it'll just measure the current. A voltmeter is similar. A voltmeter is something that I put on either side of a resistor, and what it'll tell me is the voltage drop across that resistor. So if I want to determine the resistance of a light bulb, I would put the voltmeter on either side of that light bulb, see what the voltage difference is across it, and then if I also have an ammeter and I know the current, then I can determine the resistance of that. Right? In the real world, we don't use ammeters and voltmeters, we use multimeters, which do both. And so you guys are familiar with this. We've used this before. And so this stands for direct current amperage, alternating current voltage, direct current voltage, And then we've got the little ohm symbol down here for resistance. And so all this is really a matter of changing the dial and plugging the probes in at different places to tell us both amps, volts, and ohms. Right? So multimeters are the tools that people actually use. What I want you guys to do is go ahead and write down this homework. You will be working on this for the first part of class. On Friday, you've got some conceptual ones and some quantitative ones. And so what I want to do is talk about solving complex circuits for a second. When I have complex circuits, basically what I need to do is simplify them out into simpler circuits. And so ultimately, once I get this circuit simplified, I'm going to use Ohm's law. And then I remember I can simplify resistors in series and I can simplify resistors in parallel. And so my goal is to simplify as much as I can. When I look at this circuit, I see this as my first simplification. I've got these two resistors. I've got a 45 ohm resistor and a 90 ohm resistor, and they're in parallel, so I need to simplify those first. And to get their equivalent resistance, I simply need to add 1 over 90 plus 1 over 45, and then raise that to the negative 1 power. That's an important step, and I find that this is like having 130 ohm resistor there. And I know that's a reasonable number because the equivalent resistance is always less than any of the individuals in parallel, right? And so then I can redraw this and say, okay, well, this is like having a 30 ohm resistor right there, right? That's the equivalent. And then I've got these two in series. I've got the 10 ohm and the 30 ohm. And so I can just add those together, and I know that's 40 ohms. Okay, great. And then once I have got that 40 ohms, it's like having 40 ohms here. Well, then I've got another parallel because I've got this wire coming in that splits, and I've got this wire coming in that splits. And so I need to go back and do a parallel equivalency again. And so I'll do 1 over 40 plus 1 over 60 raised to the negative 1 power, and I find that the equivalent resistance is 24 ohms right there, right? And so ultimately what I started with this big ugly circuit is like having a single 24 ohm resistor, and that's what I can plug in once I know the EMF of whatever battery that I'm using to find the current in that circuit overall. Right. I can also add capacitors to series or parallel circuits just like I do resistors. And in the next lecture, I'll talk about what we call RC circuits, which is resistor and capacitor circuits. Capacitors act exactly, almost the exact opposite of resistors. So when they're in parallel, I simply add their capacitance together. So again, when they're in parallel, if I've got like a 2, a 3, and a 4, well, I can just add those together and say, okay, that's a total of 9 capacitance. And then if I've got them in series, well, that's when I need to do the 1 over plus 1 over raised to the negative 1 power to get the equivalent capacitance of that circuit. I'd like you to also write down these homework problems. And I'll be checking these homework problems as well as those other ones on Monday, as well as your quiz, and going through those problems with you. All right, you guys have fun in class tomorrow. You'll be building circuits, working on homework, and then in the second part of class, you'll be working on that quiz.